Hello everyone. In today's module, let us learn about optical isomerism. In this module, let us learn about chiral and achiral carbons, enantiomerism, diastereomerism, mesocompounds. Please subscribe my channel, like, share and comment my videos. Let us start with sp3 carbon. Here in this sp3 carbon in structure 1, this is structure 1. In the structure 1, the sp3 carbon is bonded to 4 different carbons: bromine, fluorine, chlorine. Therefore, this is bromo, chloro, fluoro, methane. This is methane. Bromo, chloro, fluoro, methane. And in the structure 2, the sp3 carbon is bonded to 4 different groups: COOH, hydrogen, CH3 and hydrogen. This is OH. This is lactic acid. Lactic acid. And here this is CH4 methane. CH4 methane. So in this different structures, the first 2 structures are bonded to 4 different atoms or groups of atoms, and in the structure 3, the sp3 carbon is bonded to same atoms. Such carbon, so carbon with 4 different atoms is called chiral carbon or asymmetric carbon. Chiral carbon or asymmetric carbon. And the sp3 carbon which is bonded to same atoms, it is known as achiral carbon. This is achiral carbon. So chiral carbon, achiral carbon. Now let us discuss this sp3 carbon once again. So here 4 different atoms are there. So what is this substance? Bromo, chloro, fluoro, methane. And here the structure, this is structure 1, this is structure 2. In this 2 atoms are hydrogen atoms. So 2 atoms are same. 2 atoms are same. Here this is bromomethane. In structure 3, 3 atoms are same. 3 atoms are same. In structure 4, all 4 atoms are same. Therefore, this is methane. All 4 atoms are same. So, chiral carbon, what we discussed just now, a carbon with 4 different atoms is chiral. So if sp3 carbon is bonded to, even if 2 similar atoms are similar groups, it is referred as achiral. So achiral. So structure 2, 3 and 4 all are structures. 2, 3 and 4 all are achiral carbons only. So in structures 2, 3 and 4, the carbon is achiral because the same atoms 2 or more. Molecules with chiral carbon, they have a special property of rotating. The special property is rotating the plane polarized light. Rotating the plane polarized light. Rotating the plane polarized light either to left side or right side. Left side or right side. Such a property is referred as optical activity. So, optical activity is the property of rotation of plane polarized light. Rotation of plane polarized light. plane polarized light. How this plane polarized light, how the optical activity is measured? First of all, let us know what is a plane polarized light and what is a unpolarized light. So, unpolarized light, unpolarized light. Unpolarized light means light waves travel in different planes. So, this is a light, they travel in different planes randomly. Randomly means there is no particular plane for the light rays pass. So, this is a random motion. Random motion. So, such a light is referred as a unpolarized light. Polarized light means light passes only in one plane. Light passes only in one plane. Only in one plane. So, the polarized light is represented in this manner. So, this is only one plane of passing the light. Right. So, this is polarized light. Now, how to make the unpolarized light into polarized light? So, this is source of light. This is source of light. So, this source of light has light rays pass in different directions. Therefore, this is unpolarized. Unpolarized light. This unpolarized light is passing through a nickel prism. Nickel prism. Unpolarized is passed through nickel prism. Therefore, we get a polarized light. Polarized light means light waves pass in only one direction. So, this is polarized light. This is the schematic diagram of polarimeter. The different components of polarimeter. Here this is a light source. Light source gives the light rays in different planes. That is, light comes randomly. So this light comes in different planes is passed through a fixed analyzer, or this can be a nickel prism also. When the light in different planes pass through this nickel prism, the outcoming light comes only in one plane. Therefore, this is referred as a plane polarized light. And here the light comes from the source of light directly. It is unpolarized light, and here this is polarized light. This polarized light is passed through the polarimeter tube, which contains the sample substance in solution. As light passes through this sample solution and the coming out light, see here the angle changes. So the change in angle is measured in the analyzer. The changed angle is measured in analyzer. And the change in angle is measured in a degree scale. So it is a polarimeter schematic diagram. Specific rotation. The angle through which the plane polarized light is rotated by a sample of substance in its solution is called specific rotation. So the specific rotation is either to left side or right side. The specific rotation alpha depends upon number one, length of the polarimeter tube, length of the polarimeter tube, and lambda. Lambda means wavelength of the light. This wavelength of light is generally 589 nanometers, and polarimeter tube length is generally 1 decimeter equal to 1 centimeter. Temperature. Next one is temperature. Temperature is generally 25 degrees centigrade, and finally concentration. Concentration of the solution is 1 gram per liter. So under these conditions, whatever the angle through which the plane polarized light rotates is referred as specific rotation. Optical activity is the phenomenon in which the substance rotates the plane polarized light through either left side or right side. So such a phenomenon is known as optical activity. So here plane polarized light is rotated through left side. If the plane polarized light is rotated to left side, then such a substance is known as levorotatory. Levorotatory substance, and it is denoted by small letter L or minus sign. Or otherwise, if the plane polarized light is rotated through right side, then it is dextrorotatory. Dextrorotatory denoted by D or plus sign. D or plus sign. Optical isomerism is mainly divided into two categories. That is, one is enantiomerism and the other one is diastereomerism. Enantiomerism is that in which the mirror images are non-superimposable. First of all, optical isomers are those having the same formula, same structure, but the orientation of different atoms or groups differ. The spatial arrangement differ from each other. So that is optical isomerism. So optical isomers, they bear mirror image relationship. The mirror image, if the mirror images are non-superimposable, then such phenomenon is referred as enantiomerism. If the optical isomers do not have a mirror image relationship, that is, they are non-mirror images, non-superimposable, therefore they are referred as diastereomerism and they are referred as diastereomers. Now let us take an example for mirror images. So this is COOH, this is COOH, and here this is OH hydrogen, this is hydrogen OH. So what is this? This is tartaric acid. Tartaric acid. So imagine to keep a mirror here. Imagine to keep a mirror. Now, if this molecule is observed in the mirror, so the molecule is, the image of the molecule is observed in this manner. So this is OH is observed on left side and hydrogen here on right side. This is hydrogen OH. So this is the mirror image. This is mirror image. Mirror image. Try to keep this mirror image on this original molecule. Keep the mirror image on the original molecule. When the mirror image is kept on the original molecule, same groups are not coinciding. Same groups are not coinciding. Therefore, such cases, the mirror images are non-superimposable. Superimposable means same groups coincide with each other. So non-superimposable. Non-superimposable. Therefore, such non-superimposable mirror images are referred as enantiomers. This is lactic acid. Lactic acid structure is shown here. This is chiral carbon. Chiral carbon. Chiral carbon is that having all four different groups. Now, imagine to have a mirror plane. Therefore, the image is observed here. This is hydrogen OH. This is CH3. This is COOH. So here these two are enantiomers. This is mirror image. Mirror image. Now this lactic acid, it is available in two sources. The one which is available in the blood, lactic acid found in blood, has a rotation of plus 2.6. Therefore, it is a dextrorotatory. Dextrorotatory. The other one is found in sour milk. One more enantiomer is found in sour milk with specific rotation minus 2.6 degrees. Therefore, it is levorotatory. Now, let us see the tartaric acid. See here in the tartaric acid, three structures are shown. Structure 1, structure 2, structure 3. Structure 1 and 2 both are mirror images to each other. Structure 1 and 2 mirror images to each other. Mirror images to each other. Therefore, they are enantiomers. Enantiomers. Now observe the structure 3. Structure 3 is found optically inactive. Structure 3 is found optically inactive. Why it is optically inactive? See here, tartaric acid, it has 2 chiral carbons. Here is one C2 and C3. It has 2 chiral carbons. So structure 3 has 2 chiral carbons. 2 chiral carbons. Though 2 chiral carbons are there, still it is optically inactive. What is the reason? The reason is given as, see here the C2 chiral carbon, it has 4 different groups: hydrogen, carboxy group, hydroxy group, and the fourth one is this complete group. So the fourth one is this complete group. So it has a specific rotation. Similarly, the C3 carbon, it has 3 groups: hydrogen, hydroxy, carboxy group, and fourth one is this. So imagine to have a plane of symmetry. Plane of symmetry. So this plane of symmetry divides the molecule into equal halves such that each one is the mirror image of other. Each one is the mirror image of other. That means it has one of the elements of symmetry. So in such case, the rotation caused by the C2 carbon, is exactly equal to the rotation caused by C3 carbon, but both are in opposite directions. Because both are in opposite directions, they cancel each other, and externally the molecule does not show any optical rotation. So such a compound is known as a meso compound. So meso compound means the meso compound has chiral carbons, but the rotation caused by one chiral carbon is exactly equal and in opposite direction to the other chiral carbon. Therefore, internally they cancel each other, and of course optical rotation is not shown outside. That is a meso compound. Now let us see biphenyls. This is biphenyl. So this is one compound and this is one compound. Observe these biphenyls here. The plane of one benzene ring is exactly perpendicular to the other plane of the other benzene ring. In such cases, what happens? They show optical activity. So biphenyls show optical activity. Biphenyls show optical activity. But here, are there any chiral carbons? See here, all these in this benzene ring. So here, in this ring, benzene rings have sp2 carbons. So for chiral carbon, the first condition is sp3 hybridization. So all the carbon atoms are sp2. Therefore, there is no possibility of having a chiral carbon. So benzene rings do not have chiral carbons. Though chiral carbons are there, biphenyls are optically active. So the condition for optical activity is not only the presence of a chiral carbon. So presence of chiral carbon is not only the condition for chirality or optical activity. The necessary and sufficient condition for chirality of the molecule is that any element of symmetry should not be present in the molecule. What are the elements of symmetry? The elements of symmetry, there are 4 elements of symmetry. One is center of symmetry, center of symmetry or inversion center denoted by Ci. Then the second one is plane of symmetry. Plane of symmetry. This is also referred as sigma plane. Then third one is proper axis of symmetry. Proper axis of symmetry, Cn. And the fourth one is improper axis of symmetry or rotation followed by reflection. This is also referred as a rotation followed by reflection. Reflection denoted by Sn. So any element of symmetry should not be present. That means for a molecule to be chiral, all these elements of symmetry should not be present. That means even if one element of symmetry is present in the molecule, then the molecule will not be chiral. Molecule will not be chiral. It does not possess the chirality. So for the condition for the chirality is all these elements of symmetry, even one also should not present. If all the elements of symmetry are absent in the molecule, then the molecule becomes chiral. Now let us know about the difference between diastereomers and enantiomers. Diastereomers. Optical isomers are those without having chiral carbons. That means even if the chiral carbons are not present, then if the molecule is optically active, then it is referred as a diastereomer. So enantiomers on the other hand, enantiomers means diastereomers with at least one chiral carbon are called enantiomers. So diastereomers means they may or may not having chiral carbons, whereas enantiomers means diastereomers with one chiral carbon. What is the substance given here? This is bromochlorobutane. In this compound, see, 4 structures are given here. This is structure 1, 2, 3, 4. Observe carefully, structure 1 and 2 are mirror images. Structure 1 and 2 are mirror images. Structure 3 and 4 also mirror images. So what is the mirror images? But they are non-superimposable. Therefore, what is the relation between structure 1 and 2 and structure 3 and 4? So structures 1 and 2, 3 and 4 are enantiomers. They are enantiomers because they are mirror images and non-superimposable. So non-superimposable mirror images are enantiomers. Then come to other pairs. See 1 and 3. Structures 1 and 3, structures 1 and 4. They are not non-mirror images, non-superimposable. So 2 and 4. Similarly, structure 2 and 3, structure 2 and 4. So they are non-mirror images and non-superimposable. So such isomers which are non-mirror images and non-superimposable, they are referred as diastereomers. So pairs of structures 1 3 2 4 1 3 1 4. This is 1 4 1 3 1 4 2 3 2 4. They are diastereomers. Racemic mixture. Racemic mixture means a pair of enantiomers. A pair of enantiomers in equal concentrations. Equal concentrations are 1:1 concentration, or it is also referred as equimolar concentrations. Equimolar concentrations. So enantiomers which are equimolar concentrations, a mixture, it is known as racemic mixture. So a mixture of enantiomers, a mixture of pair of enantiomers which are in equimolar concentrations is known as a racemic mixture. And making racemic mixture is called racemic modification. Racemic modification. So racemic modification means making racemic mixture by mixing a pair of enantiomers which are in equimolar concentrations. Please subscribe my channel, share and like my videos. Thank you.